Yes, okay. So let's get started. Today, I want to forget about the Ram cohomology and Czech cohomology and just concentrate on the cohomology of a double complex. Okay, it's an algebraic object, and its cohomology is not always easy to compute directly. Okay, so we want to see if there are some methods that can allow us to compute the cohomology of a double complex more easily. So let's start with a double complex. With anti-commuting differentials. Uh, okay, one of them we call delta, and the other one is, okay, delta is d prime, right? And d double prime is, we're going to write it as -1 to the p of d. Okay, so here, I mean, this d for the Czech-Durham complex will correspond to the exterior derivative, but here it's just, you know, some abstract differential, okay, that goes in the vertical direction. And it's related to d double prime in this way. So, and then we form big D, you know, is d prime plus d double prime, and that's delta plus -1 to the PD. So on a double complex, you actually have 3 differentials. Okay. You have a horizontal differential, delta, and you have a vertical differential D, and then you have this big D, you know, that goes diagonally. So in fact, there are 3 cohomology groups associated to a double complex. H big D and H delta and H little d. Okay, but let me see. So there we are anti-commuting differentials, but you know, yeah. Actually, what I want to start with are 2 commuting differentials. So I'm going to say it has commuting differentials delta and d. Okay? And then, yeah, then we set d prime equal to delta, d double prime equal to this. Okay? So because delta commutes with d, and right, it's a and d goes from k to k, but it moves in the vertical direction, right? So it goes from k anything q to K anything Q plus 1. Okay, so because it commutes with, because delta commutes with D, right, it induces a map in D cohomology. So delta induces a map from in the D cohomology. Okay, yeah. On HD, which is the shorthand for HD. Okay. So it's delta is going to go from HD star Q. Let's start with 0 to HD star 1, HD star 2, and so on. Delta. Okay. So you have this map delta on HD. And like if we don't assume that this is a first quadrant double complex, then P and Q, right, they are in Z, so you can go forever in either direction. And delta square is still 0 for the induced map. And that means you can actually take H delta of HD, okay? So, yeah, you get a new differential complex, and so H delta HD is defined. And in the same way, H delta HD is also defined. HD H delta is also defined. So, associated to a double complex, you actually have 5 cohomology groups, okay? And what we want to look at today is, what are the relations among these 5 cohomology groups? H big D, H delta HD, H delta HD, and HD H delta. Okay? H big D is hard to compute because the differential is more complicated. But H delta and HD, these are easier to compute because you're only going in either the vertical or the horizontal direction. Okay? And the main theorem today is called the tic-tac-toe lemma. Okay, so so I think the best way to understand it is just with a picture. So suppose your double complex has only one non-zero, no, this HD has only one non-zero row. So this is a picture of HD. Has only one non-zero row, okay? And that will imply that H delta HD is isomorphic to H big D. So if HD looks like this, then you have an easy way of computing H big D. Okay? Nobody calls this lemma the tic-tac-toe lemma. Doesn't have a name really. Yeah, but this name was given to it by Raoul Bott, because he said like when you are working with the double complex, it's like playing a tic-tac-toe game. So he calls this the tic-tac-toe lemma. All right. So well, let's try to prove it. But before we prove it, let's try to understand what an element of H delta HD looks like. Right? So an element of H delta HD. Okay? So to be an element of H delta HD, first, it has to be in HD, right? So if you have a class in HD, okay, if you have an element A in the double complex and it defines a class in HD, what does that mean? The cohomology class exists if and only if it's D closed, if and only if dA is 0. Okay. Okay, and now you want to take the delta cohomology class of this. Okay. So this is defined if and only if, first of all, the class of A in little d is defined, and then this element should be a delta cocycle, right? So that means delta of this class of A should be the class of 0 in H little d, okay? And let's write this out. Okay, so that means if and only if dA equal to 0 and what does this mean? The way we define delta of a class is the class of delta A. That's the definition, right, of delta on HD. And so this says delta A has to be 0 in D cohomology, okay? So what does that say about delta A? Delta A is the 0 cohomology class in H little d. What does that say about delta A? When is something 0? It's exact with respect to little d. Yeah, so delta A has to be equal to dc, okay, for some c. Okay, in K. Okay? And so if you draw the picture, then you have A, okay? dA is 0, okay? And then delta A has to be equal to these. Wait, just a minute. Let me see. What do I want? dB, okay? So dB. But I like to use d double prime. So let me rewrite this as -1 to the p dB, put in a -1 to the p there. Okay, I haven't changed anything. And then this is going to be d double prime, right? And I actually like a minus sign there, so let's put a minus sign here. Uh-huh. Okay, haven't changed anything. And then let's call this C. And so this is minus d double prime C. Okay? And therefore, uh, so so this condition, right? So that's equivalent to saying that delta A plus d double prime C is 0. And so I draw this picture. This is delta, and then d double prime C. Okay? Uh, so a class, an element of H delta HD correspond to this diagram. Okay? It means that there's a little c so that you get this diagram. And whenever I draw a diagram like this, okay, okay, so if I draw a diagram like this, A1 going to something, and then here's A2, okay? So this will mean, delta A1 is equal to minus d double prime of A2, so that delta A1 plus d double prime of A2 is 0. Okay? So that's what this diagram means. Okay. All right? Okay. Yeah. Okay, so now we know what an element of H delta HD looks like. It's represented by a zigzag like this. Okay? It's very important to see these things pictorially. Okay, and so now I'm going to prove this tic-tac-toe lemma. Yeah. Let me see. So so I'm going to start with an element in H delta HD. Okay. But under the assumption that we have only one non-zero row, so HD has only one non-zero row. Well, if HD has only one non-zero row, and you take its delta cohomology, H delta HD will also have only one non-zero row. Okay. Okay, so that's the picture we start with. So since HD has only one non-zero row, say the nth row, the same is true of H delta HD. Okay? All right, so let me draw a picture of H delta HD. I don't need this. Oh, let me see. So, yeah, I have to make some assumption about the double complex. So I'm going to assume that K is a first and second quadrant double complex. So that means assume K of PQ is 0 for Q negative. Okay? So there's nothing below the horizontal axis. And I have only one non-zero row. There's nothing here. So I'm going to start with an element A0 here. A0 in H delta HD. Oh, yeah. Okay. And then, okay, no, okay, that's what H delta HD looks like. But so, okay, so that says I only need to look at the nth row. And I'm going to let this be a picture of K, all right? Yeah. So in K, if you start with an element of H delta HD, then it's represented by a zigzag. So this goes up to 0, and then you have a picture like this. Uh-huh. And the first lemma I'm going to prove is that if you start with an A0 in H delta HD, you can extend A0 to a cocycle, to a big D cocycle. Okay, so this is the lemma. This is an extension lemma. Okay. Okay, so we're always assuming that we have a first and second quadrant double complex. And so, and the only non-zero row of H little d is the nth row. Okay. And then if you start with an element in H delta HD, in the nth row, right? So it's in the nth row would be some Pn. Then A0 can be extended to a big D cocycle. To a big D cocycle. Okay. Yeah. All right. Now, if you look at the picture, it's actually quite easy to see how to do it. Okay, because you start with an element in H delta HD, so you get this zigzag. Okay, but okay, it may not be a deco cycle because when you take d of A0 plus A1, you get dA0 maybe with the sign, and then plus delta A0 plus d double prime A1 plus delta A1 plus, yeah, that's it, right? Yeah, right. You got 4 terms. And this is 0, okay? And this is 0 by hypothesis. So you get a delta A1, okay? So this goes to delta A1, and that might not be 0, okay? So you don't have a deco cycle yet. Okay? But if you go up here with little d, what do you get? If you go up, yeah, you get 0. Why do you get 0? Well, because, yeah, d and delta commute, right? So you got a commutative diagram. And so when you go up here, it's delta of this element, but then that's delta of this element. So you have delta square, and that's going to give you 0. Okay, so delta A1 is actually a deco cycle. Okay, I mean, it's obvious from the picture, but you can prove it by writing down the equation. D of delta A1 is delta of dA1 because they commute. And dA1, okay, dA1 is plus or minus delta A0. And so you get 0, okay? So delta A1 is a deco cycle. But there's no cohomology HD in that box, since HD of the box of delta A1 is 0, okay? HD is 0, so you get a cocycle has to be a coboundary. So delta A1 has to be equal to, minus d prime of A2 for some A2 in K. Okay? Yeah, okay. So you get this A2 now. And you have this picture now. You have extended your element by an A2. Okay? So now you got this picture, but when you take delta A2, it may not be 0. However, the cohomology here is 0. You can repeat the argument, right? And so delta A2 is going to come from D of something below. And you keep doing this until you reach the bottom row, okay? So let's see. So we repeat this argument until we reach the bottom row. until we extend A0 plus A1 to AN, okay, with AN in the bottom row, in the 0th row. Okay. So A0, A1, A2, and AN, and 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 you have this zigzag. Okay, and now delta AN is in this box, and by the same argument, okay, it's going to go up to 0, and there's no cohomology here, so it's going to be, it's going to come from D of something down here, but there's nothing here because we're assuming that it's a first and second quadrant double complex. So everything below the horizontal axis is 0. And so, so again, so you have delta AN, okay, is equal to minus D double prime, you know, AN minus 1, AN plus 1 for AN plus 1, you know, below the x-axis. Yeah. So below the horizontal axis. Okay, and so AN minus 1 has to be 0. And that means delta AN is 0. Okay, and so that gives you a co-cycle. Yeah, because now you have a picture like, you know, you have a picture like this, A0 going up to 0, and then A1, A2, and AN, and this goes to 0, okay? And that means you have a co-cycle, okay? So you have an extension, that's a co-cycle. Is a big D co-cycle. Okay? And now you can define this map, H, from H delta HD to H big D by sending a class A0 D delta to this co-cycle. Okay. Now, of course, you can start with a different representative for this cohomology class in H delta HD. And there are different ways of extending it to a big D cocycle. Uh-huh. So you need to show that this map is well defined. Uh-huh. But I'm going to just leave it as a homework. Uh-huh. So show that if you start with a different representative, and you get two extensions to decocycles, then they define the same big D cohomology class. Okay? And that will show that H is well defined. I mean, if I have time today, I'll actually do this. Okay, okay. And now we just need to define an inverse map, okay, to get an isomorphism. So we want to start with a big D cocycle. And get an element in H delta HD. Okay, now, so now I want to define G from HD to H delta HD. So I'm going to start with an element of HD, big D. It could be anywhere. Now we are still assuming that HD, little d, looks like this. And there's nothing below the horizontal axis. Now it's possible that, you know, we start with something like this. A big D cocycle. So a cocycle looks like that. Okay. Now the first step is a shortening lemma that says that whatever you start with, if it has anything above the nth row, then it can be shortened so that the top component is in the nth row. Okay, so we have this shortening lemma. Shortening lemma. Okay, so the hypothesis is again, let me see, right? For this, I guess, yeah, I don't need to say that it's zero below the horizontal axis. Oh, I do, because I only want to look at things. Yeah, I don't want to look at things down here. Well, Let's see. I think all I need to assume is that HD has only one non-zero row. So the only non-zero row of H little d is the nth row. And then if I start with a decocycle, if A, which is A0 plus dot, 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 whatever, is a decocycle. Okay, so I'll say if a decocycle has the top component above the nth row, if a decocycle A0 plus A1 plus dot, dot, dot has the top component A0 above the nth row, then it can be shortened in its cohomology class so that the top component is in the nth row. So that its top component is in the nth row. So until it has no component above the nth row. Okay, yeah, so let's see how we do this. Again, if you just look at the picture, okay, it should be easy. Why? Because, okay, we start with this picture, okay? And this is above the nth row. So it has no decohomology. And here you have an element that's a decocycle, right? But there's no decohomology here. What does that mean? Yeah, it's exact. So there has to be something here, B0, that maps to it. Okay? And now you just subtract big D of B0. That will kill this A0. And then you have a shorter decocycle. Okay, so, and then you repeat the process and it will stop when you reach here because now there's cohomology here. So you can't continue your argument. Okay, so the proof is easy. So since dA is 0, and the box of A, um, uh, A has 0 HD. If it's above the nth row, so A has to be equal to dB, A0, the box of A0, the top component, has 0 HD, so A0 has to be dB0 for some B0 in K, but you know that it has to be in the box below. And then if you look at A minus dB0, this will be, it will be A0 plus A1 plus dot 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 minus um, um, I better use D double prime, D double prime, okay? It has a sign built in, okay? Minus D double prime B0 plus delta B0, and then, yeah, A0 minus D double prime B0, that will be 0. That will kill off the top component, and then you have A1 plus delta B0 plus dot dot dot, and this is 0. Okay, and so you get a shorter decode cycle. Okay, so I would just say, yeah, this is a shorter decode cycle. Okay, so A minus dB0 is a shorter decode cycle. You can repeat the process until the top component is in the nth row. It's hard to write down there. You can repeat the process until the top component is in the nth row. Okay. And yeah, so that means if you start with a decode cycle, you can assume that its top component is in the nth row, and so yeah, so you're gonna have this A0 A1 and so on. Okay, you start with a deco cycle. You can start with something that looks like this, and then you can define G from HD to H delta HD by just sending A0 plus dot 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 AN to, you see here, because you have this zigzag, you know that A0 D delta is defined. So you just cut off everything else and just take the delta D cohomology class of the top component. Okay. Okay. So we'll stop here, and after the break, we'll just check that this is inverse to the other map H. Then you get an isomorphism. Okay. All right. Let's take a break. Yeah. Okay. So let's continue. Now, we have defined this map, okay, going backwards from H big D to H delta HD. Okay. You take a big D cocycle, and by the lemma we just proved, you can assume that it starts in the nth row, and you just cut off everything else, okay? And this top component, because it has a zigzag like this, it defines a delta D cohomology class, okay? But, you know, you can start with another representative of the big D cocycle. And so you have to show that G is well defined. So, so suppose you have two big D cocycles. Are D cocycles. We know with A0 and B0 in the nth row. And we still assume we still assume that we have only the H little d, the only non-zero row of HD is the nth row. Okay. Oh, and then, okay, we also need to assume that A and B define the same big D cohomology class. Oh, maybe I'll just put it here. So prove that if A and B define Okay, if they define the same cohomology class, then you want to prove that A0 and B0 give you the same cohomology class in H delta HD, okay? So, so then this would show that G is well defined. Okay, yeah, and well, H goes from this to an extension, and then G goes back to the top component, so yeah, so in one way, in one direction, they're inverses of each other. If you start with a decocycle, you go to this, and then this would be an extension to a big decocycle. And we, the previous homework says that the cohomology class is independent of the extension. Yeah, so it's easy to check that G and H are inverses. G composed with H is the identity on H delta HD, and H composed with G is the identity on HD or H big D. Okay. So this proves the tic-tac-toe lemma. That if HD has only one non-zero row, then you get an isomorphism between these two homology groups. Okay? So HD okay. Now, what if you start with HD having one non-zero column? So okay. So suppose now the picture is this. HD has only one non-zero column. And uh, and then you want to prove that there's also the same isomorphism. Okay, so you will start with an element here, right? H delta HD will have only one non-zero column, and so you start with an element here, and because it's a cohomology class in H delta HD, okay, you have a zigzag. But now you see that the same argument works because there's no H little d here, okay? So again, you can extend this to a cocycle. So exactly the same argument allows you to extend an element here to a cocycle, okay? Okay, so that will give you a map. So we can define H in the same way as before. And now suppose you want to define G from HD to H delta HD. And then, so you will start with a big D cocycle. So maybe it starts here. To the left of your column. But then again, because there's no decohomology here, so this is going to come from a B0, and you can subtract out big D of B0 and shorten the cocycle until you reach this column. Yeah, so the same argument works, okay, to prove that uh, um, yeah, you have the same shortening lemma. The same shortening lemma is true. And so again, you can assume that you actually start in this column. And then you can define G, by just cutting it off. Yeah, it's the same formula. You just keep the top component, okay? Yeah, so you also get an isomorphism when you have only one non-zero column in HD, okay? So yes. Okay, so we get this theorem then that if the double complex has nothing below the horizontal axis, and H little d has only one non-zero row or only one non-zero column, then H delta HD is isomorphic to H big D. Mhm. Yeah. Okay. Now you can reverse the row of delta and D, right? You can switch them. So by symmetry, right, you get another theorem. This is another tic-tac-toe lemma. So by symmetry, now if you switch, if you just reflect the picture about the diagonal, so P goes to Q, Q goes to P, delta goes to little d goes to delta. So then instead of this hypothesis, then you will assume that you have nothing in the what? For P negative, right? So, yes. And so what would the theorem be? Can somebody state the theorem for me? I can switch delta and D, right? I switched horizontal and vertical. So the theorem would be if H delta has only one non-zero row or column, then I switch delta and D. H D H delta is isomorphic to H big D. Okay. 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 So when would both of the theorems be true? So if you want both theorems to be true, then the hypothesis should be that you have nothing below the horizontal axis and nothing to the left of the vertical axis. So that means you have a first quadrant double complex. Okay. Yeah. So we get this theorem, combining the two, you have the theorem, assume that K is a first quadrant double complex. And then yeah. Okay, so yeah, so then HD has only one non-zero row or column. It's going to imply that H delta HD is H big D, and H delta has only one non-zero row or column, will imply that H delta is isomorphic to H big D. Okay, and so so if both of the hypotheses are true, then you have two ways of computing H big D. Okay, then these two will be equal. Okay, okay. So let's apply this to the check dilemma complex. So the check-Delam complex looks like this. So you have omega, no, you have C0 U omega Q here goes to C0. Here is 0. And no, here's Q. Qth row goes to C1 omega Q. And it comes from C0 omega Q minus 1. Okay, so that's the check-Delam complex. And let's first compute H delta. Well, you know that each row is just a generalized Mayer-Vittora sequence. So it's going to be exact except here because you're missing the kernel, right? So when you take H delta, you will have, in here, you'll have the kernel of delta, which is the global forms. You'll get HQ of M, and then everything else is 0. HQ minus 1 of M. Okay, so you see that H delta has only one non-zero column. And so that means H big D is isomorphic to HD H delta, right? If H delta has only one non-zero column, you have this, and that is going to be, if you take, oh, sorry, this should be the global forms, right? The kernel of the difference map, yeah, is the global forms. And if you take HD of this, then you get the Ram cohomology. Okay. Okay, now let's do it the other way. So let's compute HD first. But doing it the other way, you need to assume that you have a good cover. So if U is a good cover, then what is HD? Well, let's see. Oh God, where is it? Yeah, this is a check-Delam complex. And now we are looking at the cohomology in the vertical direction. And so each open set is diffeomorphic to Rn, and therefore the cohomology in the vertical direction is all 0, except in degree 0. So H0 will be all 0, except in degree 0, where you have the kernel of D are the constants. So you have this. Okay, the locally constant functions on the open sets. So that's HD. And then H delta HD will give you check cohomology of the open cover. So you get H0 of the open cover, H1 of the open cover, and so on. And then because HD has only one non-zero row, this is isomorphic to HD. Okay. And so you see that the cohomology of the check-the-RAM complex can be computed as H delta HD. Then you get check cohomology, or it could be computed as HD H delta. In that case, you get the RAM cohomology. So they're equal. And what does that give you? So you know, so if you look at degree n, okay, degree n would be all the anti-diagonals that sum up to n. Okay, okay. So, but it's all zero except down here. So degree n would give you h, the check cohomology in degree n of the open cover. And then here, degree n would be the nth, the RAM cohomology. So using the tic-tac-toe lemma, then you get very easily the check-the-RAM isomorphism for an open cover, for a good cover. This is the check-the-RAM isomorphism for a good cover. Okay? Yeah. Okay. So we'll stop here today. Yeah. So there was a homework problem that was originally assigned, you know, for homework 4 that asks you to calculate the cohomology of CP1. And you can use this kind of argument, you know, to calculate that cohomology in two ways. One way, it would give you the RAM cohomology, and the other way would be not quite check cohomology, but it's simple enough that you can just calculate it. You know, you can calculate H delta HD and H delta. Okay, yeah, we'll stop here today.